Have you ever really stopped and wondered what's actually happening inside your computer? I mean, deep down, at its very core. Well, today we're going to pull back the curtain on the secret language of machines, and it all kicks off with one very simple question.
It seems kind of impossible, right? How can a simple switch, a choice between on and off, or a yes and a no, end up creating streaming movies, complex video games, and pretty much everything else we do online? That is the big question we're going to tackle.
And you know what? The answer, as it turns out, is actually beautifully simple. It's all about building incredible, mind-boggling complexity from the most basic foundation you can imagine.
Yeah, that's it. The entire digital universe. Every photo you've ever taken, every song you've streamed, every single line of code is built on this one simple idea, a choice. And in the world of computers, that choice gets a special name. It's called a bit. Think of a bit as the atom of information. It can be a 0 or a 1, an off or an on, a false or a true. Now, on its own, a single bit isn't very powerful, but it is the absolute starting point for everything. So, if a bit is like an atom, how do we start building molecules? Well, the whole trick is that we group these bits together into standardized chunks. That lets us represent more complex ideas. Let's take a look at the first few of these building blocks.
First up, and this is a great name, we have the nibble. It's just a little group of 4 bits. With those 4 bits, you can create 16 unique combinations of zeros and ones. That's just enough to represent things like a single hexadecimal digit.
All right, now for the big one. Probably the most important data structure of all, the byte. A byte is a group of 8 bits, and it's the fundamental unit for processing and for memory. What that means is, when your computer's processor needs to go grab a piece of information from its memory, the absolute smallest single chunk it can ask for is 1 byte. And this illustrates that building block concept just perfectly. What you're looking at here is a standard 8-bit byte. But what's really cool is how it breaks down. You can see it's literally made of 2 4-bit nibbles just sitting side by side. The one on the right is the low-order nibble, and the one on the left is the high-order nibble.
But why stop there? We can keep going. If we group 2 of those bytes together, we get an even bigger 16-bit structure called a word. Let's see how this all stacks up. So here's the full 16-bit word. At first glance, it just looks like a long string of zeros and ones, right? But it's got a hidden structure. And there it is. See? Just like a byte was made of 2 nibbles, a word is simply made of 2 bytes. You've got bits 0 through 7 making up what's called the low-order byte, and then bits 8 through 15 making up the high-order byte. And if we take it all the way down, you can see the whole family tree. One 16-bit word is made of 2 bytes, which are in turn made from 4 nibbles, and those are all just collections of individual bits. See? It's just simple blocks stacked together to build something bigger.
Okay, so we have these structures: bits, nibbles, bytes, words. But how do they actually mean anything? Well, let's start with the most basic concept there is: numbers.
Let's circle back to our old friend, the 8-bit byte. With 8 bits, where each one can be either a 0 or a 1, you can make 256 unique patterns. And that allows a single byte to represent any number from 0 all the way up to 255. And this isn't just some abstract theory. This has real-world consequences. Ever play an old-school video game like Pac-Man or The Legend of Zelda and wonder why you'd hit a limit of 255 rupees or see weird level glitches? It's because the programmers were literally using a single 8-bit byte to store that number, and once it hit 255, that's it. It couldn't count any higher. But wait, what about negative numbers? Well, computers have a pretty clever trick for that. For what we call signed numbers, they just take those 256 possible values and basically split them right down the middle. So instead of going from 0 to 255, a signed byte represents numbers from -128 all the way up to +127.
So computers can store numbers. That's cool. But the real magic is that they can also do math with them, using incredibly simple rules at lightning-fast speeds.
Check this out. These 4 lines, that's it. That is the entire rulebook for adding in binary. 0 plus 0 is 0. 0 plus 1 is 1. The only one that's a little different is 1 plus 1. That equals 0, and you just carry the 1 over to the next column. Exactly like carrying the 1 when you do regular addition on paper.
So when a computer adds 2 numbers, it's not doing anything magical. It's just following those super simple rules, column by column, from right to left, carrying the 1 whenever it needs to.
The difference is it does this millions or even billions of times per second, which is how it can perform such complex calculations so fast.
Okay, now for the final leap, the big aha moment. This system, this whole language of zeros and ones, isn't just for numbers. It's used to build literally everything we see and do on a computer. I mean, this is the real takeaway. The same system of bits and bytes represents numbers, sure, we've seen that, but it also represents every letter of text on this screen, using a standard code like ASCII. It represents the color of every single pixel in a photograph. It represents every note in a digital song. It even represents the very instructions that tell the processor what to do next. It's all just zeros and ones.
So when you really think about it, the entire, vast, complex digital world, from the smartphone in your hand to the massive servers that run the internet, it's all built from an endless string of the simplest possible choice you can imagine. 0 or 1, on or off, yes or no. It's pretty incredible when you stop to think about it, isn't it?